Greetings, Earthlings. This is Alan Boyle, Aerospace and Science Editor for GeekWire, and I'm here with Chris Lewicki, the Chief Asteroid Miner at Planetary Resources. And today we're going to take a tour of Planetary Resources' secret headquarters.
No longer secret. We're the first worldwide tour here. We'll give you a walkthrough today. We'll show you where the magic happens. We'll show you our next Arcid 6 spacecraft headed towards space, and a little bit of how we're working towards our mission of expanding the economic sphere of humanity into the solar system.
Well, let's get started.
All right. So you are in our lobby. You walk in and you are greeted by Boba Fett, of course, from Star Wars lore. We named our spacecraft after things that are in Star Wars. This particular one is on loan to us from an investor who is a very, very eager collector of a lot of different Star Wars things. You'll see a few more things like this on the tour.
So I know Elon Musk has a statue of Iron Man at SpaceX, and people have compared Elon Musk to Iron Man and Tony Stark. Does this mean that you're Boba Fett?
I don't think so. Bounty hunting isn't really kind of in our central business. It's more the prospecting part. So the Aerokid Industries Model 101 Viper probe droid looking for resources in asteroid belts around solar systems is more what we're about.
Okay. Let's see the reality.
All right. Well, let's start on the tour. So we have here in Redmond, Washington, all under one roof, our engineering, our operations, our manufacturing, as well as then the ability to talk to the spacecraft once it gets up into space. So we're walking over now, kind of around into our operations area. And in our operations area, we have Brian and Brian. Hi, guys. Hello. And they are working right now doing day-in-the-life testing on Arcid 6A, which is our next spacecraft scheduled for a launch on an upcoming SpaceX launch out of Vandenberg Air Force Base. And in day-of-the-life testing, we essentially go through everything that the Arcid satellite will experience once it's released from the launch vehicle and it starts orbiting the Earth. And you can see some simulated orbits here. It is in a polar orbit. In our simulation here, it's just over Russia and Siberia, up near the North Pole, headed eastward. One of our investors and technical partners is 3D Systems Corporation, and 3D Systems is one of the largest additive manufacturing companies in the world. We've been working closely with them on the technology to create more efficient, more affordable, more manufacturable satellites. And we also use it for a lot of prototyping activity. This is some work we're doing for the next instrument we're developing for the Arcid 100. And we can use this with other technologies to be able to print something with a 3D printer. Here's an example of an idea for a propulsion tank on our Arcid 200 satellite. And going from something that's very high resolution print like this with lots of detail and integrated structures and all the things that make spacecraft complicated and expensive to build, simplify that down into one piece, and then be able to make it out of aerospace titanium. And this is one technique we've explored in doing this. We're also looking at other techniques where we use direct metal printing, where we don't have the plastic part in the middle. And that leads to something fun we did earlier this year. We took one of the biggest resources in space. This is an iron meteorite. This particular one was recovered in Argentina, initially discovered over 100 years ago. And this is mostly iron, a little bit of nickel, a little bit of cobalt. But you should think of this as space-grade Iron Age material. And what we're able to do is take this material and process it into a powder, leaving everything the same, not doing anything to change the chemical composition of it. And then in one of 3D Systems printers, we're able to directly print a structure straight out of asteroid material. So this object, which is a complicated little example of a structure that you might build in space, was the first object ever created from materials that did not originate on the Earth. Here we're standing outside of our electronic fabrication area. We call it EFAB for short. And on the desk in front of you, you see what we call FlatSat. And this is all the innards and guts of the Arcid 6 satellite, every piece and component that makes the satellite work. This is the underlying asteroid detecting technology that we have developed nearly 100% in the building that we're going through and touring today. Our team of 50-plus engineers has built all the designs of this. We've prototyped it. We've pulled it together and built every component of this. In some cases, sourcing things from consumer electronics, mobile electronics, industrial sources. But really, this is the key to lowering the cost of deploying businesses in space, whether it be asteroid mining and prospecting, or even things for doing Earth orbit, Earth observation.
Wow. How high is the ceiling here?
I think it is just a little bit under 30 feet. This is our manufacturing area, and why don't we step back here? So in our manufacturing area, over here we have computer-controlled milling machines, and we have a staff of technicians which can take the designs straight from the engineers, program them in the machines, and then make all the pieces that we need. So if of course, everything goes right. We put the part right onto the satellite. If it didn't work out, we can make the correction right here in the building. And these computer-controlled machines, along with a lot of the older standard stuff, allows us to very quickly iterate, prototype, try things out, and really be able to control our own schedules for doing this. So we're very happy that we also have this under one roof. On the other direction here, we have our environmental test area. And this is in a thermal vacuum chamber. And I'll just step over here. In the thermal vacuum chamber, we take the components for Arcid 6 and the satellite itself, and we can put them in this chamber. We can pump out all the air, so it's like the vacuum of space. And then we can also make it very, very hot or very, very cold with the liquid nitrogen that we have here. And this helps us simulate the hot and cold of space and the way that things heat up and cool down. And of course, in space, in a vacuum, heat moves a little bit differently than we're familiar here on Earth. You can't just put a fan on it and cool it down. There's no air to blow. So one of the biggest design challenges, of course, is making that thermal design work. With Earth orbit, when you're going through thousands of hot-cold cycles, 18 of them a day, and when you get out into deep space, it's a very harsh thermal environment. So here, just like we can do tests of the software and the other systems to make sure that the programming is right, we can make sure in our thermal vacuum chamber that the design is right, and that design will be able to survive the very, very unforgiving environment in space.
So we'll have to get suited up?
Yeah, we will.
We'll put on the bunny suits?
We'll put on the bunny suits. We'll get electrostatic discharge wrist straps and face masks. And I think what we'll do first here is wipe down all the camera equipment. More sticky mats, so we get ourselves even more clean here. And now we're in the clean room.
Who cleans the clean room?
All of the staff. We have clean room days, and you do have to mop it. We do wipe down the walls. We have filters in the ceiling that we change. And this room is held in positive pressure, which means that it's actually pressurized so that everything kind of flows out. So any dirt or dust that accumulates here can get pushed out through the cracks in the doors, so we don't have to worry about anything coming in. And here are the stars of the show. Our two Arcid 6 spacecraft. We have Arcid 6A on the right here, Arcid 6B on the left. And let's step up and give you a tour. So here's where we clip in. Make sure that we're grounded.
So there's no static electricity that can harm the spacecraft.
So we're standing in front of the Arcid 6 spacecraft. These are the next in our roadmap of technology that we're developing to prospect for resources on asteroids. And the Arcid 6 build upon what we learned in the Arcid 3 and 3R, and we have the next iteration of a lot of the different systems. These are systems that we use to compute, systems that we use to keep the satellites pointed, know where they're pointed. You can see on the outside here the solar panels, which some of them are fixed, some of them deploy through mechanisms. We have the radio systems. We have things that we use to communicate with Earth, of course. We're using RF radios for doing that now. In the future, we'll transition to optical comm. And the feature of both of these satellites is the first ever commercial mid-wave infrared imager. This is an imager that we're deploying to Earth orbit which can help us detect water and water-bearing minerals on asteroids. When we point it down, we can help detect that process on the surface of the Earth. So ARCID 6 will test that in Earth orbit as a first step, and this helps us provide really global Earth intelligence with a spectral capability to provide actionable insights and really a lot more data that you can't really see. We can see the unseen with this sensor, and ARCID 6 will be the test of it. So this is our break room and lunch area, and everybody is having lunch now. So we have team meetings here. People lounge out on the couches. We've got all of your startup normal stuff, ping pong tables, pool tables. But I have to feature, of course, the vintage asteroids game.
Well done.
You can see who has the high score. The high scores are currently pretty low, so the power must have been reset on it. But we've got asteroids, we've got Star Wars pinball machine, we've got Star Wars video game over there. And this is just a really fun thing. I mean, we're a family here. Everyone's very close with each other. We like to eat lunch here and sometimes eat dinner here. Let's continue on upstairs. We'll go this way.
Okay.
And, we like graphics. So we've got lots of commemorative posters. We've got, a relatively famous spacecraft
Right.
that's been developed.
That's the ARCID 6000.
This is the YT 1200 freighter, otherwise known as the Millennium Falcon. And then this is upstairs.
So you mentioned that there are about 50 employees. How many have had experience at NASA? Did you bring over people from JPL when you?
Yeah, so a small amount of our team has deep experience of NASA, myself included as a system engineer and flight director for Spirit and Opportunity. Our chief engineer, Chris Voorhees, led the team that built Curiosity, and he's leading the team that's building all our spacecraft. We have a number of other individuals that participated in the design of almost every U.S. mission that headed to Mars, as well as the Hubble Space Telescope, Planet Mercury, and a few others. But it's not just about space expertise. It's also about mobile computing, software, other innovative approaches. So we have people from Intel Corporation, as an example, whether it's bus systems or the Core i7 line. We have people from the mobile computing and even the gaming world. And we also have people that are just right out of college that we've brought in for co-ops and internships. We're always hiring. We have an internship program we do twice a year. We usually get hundreds of applications, and we have less than 10 spots each class at the moment. So very competed for.
But this is your rapid prototyping system?
This is our Lego prototyping system. So Super Star Destroyer in this particular case. So let's continue here.
Yep.
So we've just seen in the clean room the ARCID 6. The ARCID 6 is our next step in our technology development path. Each of these satellites are directly contributing to the next one. On the table here we have a prototype of the ARCID 100, and this really is the core of what we need to get to the asteroid to identify the resources and materials on it. And in Earth orbit, it's a test bed, but also a business. The Ceres constellation will allow us to use this technology to take the same technology to monitor resources on asteroids, and we can manage and monitor our own planet's resources with this. When the ARCID 100 and the Ceres constellation are fully deployed and complete, we'll have demonstrated nearly all the technologies that we need to get out to asteroids, and we'll continue by adding this technology onto the ARCID 200. This is a full-size prototype. It's not any bigger than this. And around the top here is the technology that we use to point and control the satellite. The same electronics that are in the ARCID 6 are going to power this spacecraft. The same sensors that are in the ARCID 6 are going to be the eyes of this spacecraft. And we'll add the propulsion that we need to leave Earth orbit to get there, and also the optical communications technology. So this is just like you would develop various versions of a software, going from a prototype to alpha to beta to version 1, and then incremental revisions.
You're at Windows 10.
Yeah, so it's the same type of philosophy though, and there's no reason now with hardware, we see this in mobile computing, rapid iteration, new features coming on all the time. We saw the opportunity to do this with spacecraft, and going from ARCID 3 all the way out to ARCID 300 is our completing that roadmap, and excited to be making progress on that roadmap every day.
Well, this is great. Thank you so much, Chris Lewicki from Planetary Resources, for showing us around. Be sure to read the whole thing on GeekWire. We're going to talk about planetary resources for years and years to come, I have a feeling. So for GeekWire, I'm Alan Boyle, Aerospace and Science Editor, urging you to watch the skies.
Thank you.